Example 3.2.5, two generators are providing power to a common load. Generator 1 has a no-load frequency of 62.0 Hz and a frequency power slope of 1.2 megawatts per Hertz. Generator 2 has a no-load frequency of 60.3 Hz and a frequency power slope of 1.0 megawatt per Hertz. The two generators supply a real load totaling 3 MVA at 0.9 power factor lagging. Draw and label the PF house diagram for the system. At what frequency is the system operating and how much power is supplied by each of the generators? Suppose that an additional 1 megawatt of load is added to the system. What will the new system frequency be and how much power is supplied by each generator? For the system configured in C, what will the set point of Gen 2 be adjusted to restore the system frequency to 60 Hz? Got a lot of solving to do in this one, but this is pretty representative of small power systems. We've got a generator. It is connected to a second generator, and together they serve the common load. They're sharing the load. And by analyzing this allows us to build up to larger power systems. So how much P is flowing from this direction, how much P is flowing from this direction is a good question. P1, P2, and then what's the frequency, FSys, of this system? So we'll use the FP diagram, the frequency and power droop characteristic that we used in example 3.2.4. We'll use the same method, but this time we have to analyze it for two generators. So that's a big overview. Let's summarize the givens. From the problem statement, we've got generator 1's got a no-load frequency where the generator set point is at 62.0 Hertz. Its slope characteristic, its frequency droop characteristic as it's often called, SP1 is equal to 1.2 megawatts per Hertz. And then we've got the second generator, its no-load frequency set point is 60.3 Hertz, so a bit lower. And its frequency droop slope is 1 megawatt per Hertz. SP2 is equal to 1.0 megawatt per Hertz. So again, FNL1 and FNL2, those are the generator set points. We can change those. SP1 and SP2 really are more related to the construction of the generator. The last thing we know from the problem statement is that the load is 3 megavolt amps at 0.9 power factor lagging. Magnitude of S is going to be equal to 3e to the 6 volt amps. The power factor is 0.9 lagging. So we are asked to find the PF house diagram. I'll explain what that is shortly. We want to know what the system frequency is, right? They're all connected together on a bus, so they all have to have the same frequency. We want to know what the power provided by generator 1 is. We want to know what the power provided by generator 2 is. We want to know what the FSys new is with P total plus 1 megawatt. So the power being provided increased by 1 megawatt. Then we want to know what the new shares of power are. P1 new, P2 new. And then we want the last part. Question C said, or question D says, well, what does the generator set point need to be adjusted to restore the system to 60 Hertz? So that's just asking if we're only going to change one of the generators and we're going to do two, what's the no load frequency 2? What do we adjust to fix this frequency problem that's going to arise? Okay, so in part A, we were just asked to draw the PF house diagram. So a PF house diagram is just two back-to-back frequency droop characteristic plots, and we mirror one around the y-axis or the frequency axis. So again, we have a electrical frequency as our y-axis and power as our x-axis. Instead of just extending in the positive x direction, it also extends in the negative x direction, although both of these are positive numbers. So this represents the power plant 1, this represents power plant 2. Still in the very middle, that's 0 megawatts. Right? So we need to plot the two frequency droop characteristics. So we go up to our givens, we see that power plant 1 had a frequency droop of 62, and power plant, or had a generator set point of 62 rather, and power plant 2 had a generator set point of 60.3. So we need to draw those points right here. That's 62. And that is 60.3. So the slope's going to look like that. That's SP1, since it's associated with power plant 1. So that's 1.2 megawatt per hertz. And then we've got another plot that goes in this direction, and that's SP2. And that was 1 megawatt per hertz. So what's going to happen is we are going to find a point P1 and a point P2 where those two together, added together, equal the total load power, right? The total power delivered by the two generators summed together has to be equal to the total power demanded by the load. So if I had drawn these correctly, which I didn't, but if I had, if we drew this line straight across here, like that, P1 plus P2, that's where those lines will intersect. So sorry it's a little messy. It's hard to erase on this tablet, but anyway, the balance of power comes from basically that diagram. Make that a dotted line real fast. It comes from that diagram right there. You find P2, that should be P1, and they have to have the same frequency. That's what's common amongst these generators, is the frequency right here. So this is F sys. So that leads us to basically one governing equation. P load equals P1 plus P2. We have individual equations for P1 and P2. That's P1 equals SP1 times F no load 1 minus F system. And then we have P2 equals SP2 times F no load 2 minus F system. And in these equations, these were given, these were given, these have to be the same number. So we can just, in essence, write the equation by substituting these into these right here. So P load from the problem statement was 3 megavars, not megavars, megavolt-amps, had a power factor of 0.9. That gives me 2.7 megawatts of real power. Remember, these plots are just, frequency droop characteristics are just in response to watts. So we say 2.7 megawatts is equal to P1 plus P2. So we can go start to sub in numbers. That's 1.2 megawatt per hertz for the frequency droop characteristic of Gen 1. The no load set point was given to us as 62 hertz. We don't know system frequency yet. That's what we're trying to solve for, F sys. And then we need to add on P2. Its frequency droop characteristic was 1 megawatt per hertz. Its y-intercept was 60.3, or its no load frequency was 60.3 hertz. and then they have to have the same frequency, so FSys. So now all we have to do is solve that problem for FSys. So if you do all that math, you get 60 hertz. I encourage you to go through the algebraic steps on your own to confirm that. So we get FSys is equal to 60 hertz. Now we can determine the share of power that the two generators provide. P1 is going to be equal to 1.2 megawatt per hertz times 62 minus 60. So that's 2.4 megawatts. And P2 has to provide the remainder, so that's 2.7 minus 2.4, so it's 0.3 megawatts. Could also solve it from 1 megawatt per hertz times 60.3 minus 60 is 0.3 megawatts. So P1's providing by far the lion's share of this generation. In part C, we are asked to determine what happens to the system frequency if the load increases by 1 megawatt. So that's P load is going to be equal to 1 megawatt plus 2.7 megawatts. And nothing else in that equation changes. So that's still 1.2 times 62 minus FSys plus 1 times 60.3 minus FSys. And in this case, we can solve for a system frequency of 59.5455 hertz, so a little bit of a decrease in system frequency. The system power is going to be 1.2 times 62 minus 59.5455. That gives me a Gen 1 power of 2.94545 megawatts. And P2 is going to be equal to 1 times 60.3 minus 59.5455 equals 0.754545 megawatts. So most of that uptick in generation we can see what the changes were. Went up by 0.5 here and 0.45 here. So then the question is we need to restore system frequency. We do that by changing the no-load set points of the generator to move these curves up. We have three control strategies that we could implement for this system. We could change Gen 1, we could change Gen 2, or we could change both Gen 1 and Gen 2. And changing both generators in response is a somewhat, there's no reason it wouldn't work, but it's just a difficult math problem to solve. It's easier to solve the math problem if you just decide to change one of the generators. And so what we're going to do, or what we were asked was, okay, let's compensate for this decrease in frequency by changing the set point of Gen 2. So what we're going to do is we're going to be moving, we're going to increase its no load frequency above 60.3. And we need to know, well, to what value. And so to do that, we know that the total load, again, is 3.7 megawatts. That's going to be equal to 1.2 megawatts per hertz times the set point of Gen 1, which is remaining unchanged in this scenario, 62. Now we want FSys to be 60 hertz, so we're going to plug that in, 60 hertz right there. And we get the frequency droop characteristic of Gen 2, which was 1.0 megawatts per hertz. And we need to multiply that by its no-load set point. That's what's changing in this problem. So you have to understand generator operation to understand that that's the variable we're solving for. And then we subtract off 60 hertz. So we just need to solve all that for no-load 2, and we get F no-load for Gen 2, where the generator set point needs to be increased to 61.3 hertz, and that will restore total system frequency to 60 hertz. for a load of 3.7 megawatts.